And looks like we can start. Welcome back, everyone. Well, we are on our very last week for the course, so that's definitely exciting. We are now on week 15. That's pretty much where everyone wants to be when getting into linear algebra. But any questions at all, folks, before we get started? Okay, let's run through the announcements today. Looks like it might be a Zoom only class, but that's okay. This is kind of a tougher week. So if you're a little bit busy, you have to come in through Zoom or watch the YouTube video later. No worries, I get that. No judgment. So running through the announcements for today, I'd say we're mostly done with section 6.1. We should be completing this before very long today. After we move through this section, we're going to go into the review for the final exam. And the final exam is only going to go up to section 6.1. That's where our course is going to end. And for the curious, if you want to know what the rest of the course would have been if we didn't have any snow days or sick days, that kind of stuff, they're right here in this document. So you can click on there, take a look at those notes if you would like to. But let's see. As far as studying for the final exam, if section 6.1 is going to be the last section we're covering, I felt like I should give some practice exercises. That's those right here listed out. And also a bit of a hint on the real final exam. I'm going to ask a question that's similar to the one you'll see on example 8 of those notes. I have another question just like that on the review, so I'll make another mention it when we go through those problems. But that's going to be our big question that we try to answer that culminates everything in section 6.1. Other things that I added to these notes here are the extra credit opportunity does end on Friday for the course evaluation, but also for the extra credit opportunity relative to the final exam, I did make a change here. I've said that if your final exam score is higher than the minimum score, then the final exam score will replace it, but I wanted to be more specific. I do curve the final exam in an amount that makes sense. I don't want the average grade of the class to go down because of the final, so I usually do curve it. And when I curve the final exam, it's going to be the curved score that replaces your minimum score amongst exams 1, 2, and 3. So I felt like I wanted to be just more specific about that right there. And by the way, if you're studying for the final exam, you definitely want to take a look at this right here. This is the real last page of your final exam. It'll give you an indication of what formulas, theorems, definitions are provided, and it will also help you decide what is the stuff that we have to memorize for the exam, the information not on there. In fact, when you do study for the final exam, it might be a good idea to have 2 pages. One page is going to be your scratch work. So over here is your one page where you're doing all your linear algebra. But your second page should be a formula sheet. Not the formulas on this document here, but the formulas that you noticed you actually needed to use when you were studying. That'll be a great way to retain that information, and it'll help jog your memory when you see those problems again on the real exam. Any questions at the moment, folks, with those announcements? Okay, let me go to the actual Moodle website. Other things to mention that are new on the Moodle website are exam 3 did get graded. This was a pretty long weekend for grading. The average score came out to 79.2%, which was not terrible for a tricky exam, but the maximum grade was 87%, and that's my indication that exam 3 was definitely pretty nasty. Because of the maximum grade right here that I decided to add this emphasis, when I curve the final exam, it'll be your curved score replacing that minimum. Since that was an indication that the exam was extra challenging, I'd say. Any questions about the exam folks would like to discuss? Okay, well, moving on to the last part of the announcements. Let's see here. If you move to the very last part of the Moodle website, this is the last page of the final exam that we mentioned, the formula sheet. I also put blanked out exams 1, 2, and 3, mainly because these are excellent for studying. If you can come back here and say, solve exam 1 completely cold, meaning no use of notes whatsoever, then that'd be your indication you really do have great retention on exam 1 material, and then just move down the line. Circle any questions that you feel like you're struggling on, and you can ask me about them. Things like what section should I look into, where should I study to help with those questions. And this will be a good way to indicate to yourself, what are the hard parts of the actual course that I need to focus on? Hello. Then this one right here, the next resource, Sample Final Exam Problems version 2. These are just the blank lecture notes, and we've been using them for quite a while for our exam reviews. But again, if you come back, let's see where, there it is, the eraser. If you come back here, it wouldn't be more you're trying to solve all the problems in that. That's the entire course. So that's a lot of problems, probably more time than you actually have. The way to use this document is, you notice that there's an area that you just need more practice in amongst these content here, exams 1 through 3. Send me an email and I can tell you what section to take a look into. And then you can open this document and just target that specific section. Maybe it's, say, section, let's scroll down to 1.5, for example. This one was a pretty challenging section. It had its own idiosyncrasies like parametric vector form we had to be careful about. So that would be the purpose of this document here. It's 30 pages, so again, you're not meant to solve every single problem, but it's more for targeted practice. This document is sample final exam problems that, again, these have been here the whole time. These are older problems. I started teaching linear algebra almost 10 years ago. Wow, time flies. And so these were the very first problems I put down as review problems. Some of them might look like they're a little bit rough, but they are still good extra practice. But I would only use this document if you're just running out of things to study, or maybe you're really bored, you want to find more things to work on. That would be a good document. Finally, last but not least, this is a real final exam that I gave in the year spring 2022. I post these to give you a good feel for what your actual final exam will look like, because it is hard going from a 75-minute timed exam to a 2-hour timed exam. There's an adjustment period there. I would say don't read anything over here. The rules for your exam are still the same. For example, this one didn't have use of calculators, but ours is open calculator. The rules did change from 2022. So going through here, you'll get a feel for what a real exam would look like, the type of questions you're going to be getting into. Common questions folks have is, what's the length of the final exam? That's hard to answer because, I mean, question number 12 is really fast. And question number 11, well, that one could be a longer question, finding all the eigenvalues. So giving you a number of questions isn't the most important information. This one had about 14 questions with the extra credit, but it's targeted at a certain amount of time. I've tried to write a final exam that's about an hour and a half in length. So there'll be about 30-ish minutes for you to double check your work and that kind of stuff. So word of warning, this last exam right here, that's a dangerous document for reviewing for a final exam. It has its own traps. The way I write my final exam is I go to documents like this one. And I scroll through here because these are the problems that we solve. And all I'm doing is taking a representative sample of questions from section 1.1 all the way through section 6.1, the last one we're on. So that means the questions that are going to be asked on our real final exam might look different than these questions. It's always going to be kind of a new random selection of different assorted questions, but they all come from a general test bank like this one. So my warning is, if this is the only document you're studying from, then that's a dangerous way to study for the final exam. There could be huge areas you're missing because I can never ask every single question on the final, and I don't necessarily always ask the same questions. This is more just here to give you a feel for what does a final really look like. That's a lot of talking, but any questions at the moment? Okay, oh, we've got a chat. Prem asks, will it be similar in the form of the final exam offered in spring 2022? It'll be similar in form, but not necessarily the same questions. Some of those questions could be different. They all come from exams 1, 2, 3, and I look at this document in particular in selecting those questions. Does that make sense about that question there, Prem? Awesome, glad to hear that. Any other questions so far? Yeah.
So in theory, if we're able to solve all of the problems on the blank lecture notes, will be okay. But it's a better strategy to look at the blank exams and do it that way.
Yeah, that's a great way to say it. Looking through here, you're saving a lot of time if you're studying those particular problems. And then it tells you where your areas you should look into further. But you're absolutely right in your first statement that this is to me like the test bank that I use to build our next final exam that's coming up. So if you could get through those questions there, well, you're going through the entire class. That's not necessarily a bad way to study. It's a time constraint though, but you would be in excellent shape for the real final. Other things to mention though is keep in mind where exam 3 actually ended. Exam 3 ended, let's see here, in section 4.5. That means you do want to pay a little bit of extra attention to sections 5.1, 5.2, 5.3, and 6.1. These are the sections that weren't actually on any exam at all. And so I would give those just a little bit of extra study to make sure we're on the right track. I do understand that this is the one section I'm not even grading homework on. So that's why I put out this massive hint. If you can solve the last question on these notes, then you're in great shape for the final exam. As far as sections 5.1, 5.2, and 5.3 go, I understand it has never been on a final exam, those content. So when I write a question for these, I look really closely at this document once again, that's like a test bank. And then I look really even closer at the actual problems that you solved on the homework assignment. I want to make sure that there's a good overlap between the homework assignment problems that you did and the actual lecture notes. So good questions would be from here as well. All that to say, if you're studying for the final exam, take another look at your homework sets from section 5.1, 5.2 to 5.3, and that would also be an excellent way to study and be prepared for those sections. Any other questions so far, folks? Okay, well, that was 11 minutes of announcements, but those were great questions and I think important announcements, I hope. Let's now finish off our last section of the course, section 6.1, and then we'll switch gears to the review. When we come back on Thursday, that's all we're going to be doing, reviewing, and we'll probably finish out this document here. But I also want to extend an offer. There's a question that you want to have us take a look at as a class. Don't hesitate to ask. It can come from anywhere, somewhere from here, somewhere from the book, maybe online. I'll be happy to include it in our review. But if we run out of class-directed questions, this is just my backup right here for questions that are good quality still. So now in section 6.1, finally, after all those announcements, here's where we left off. What we did was we defined the dot product between the two vectors. We also defined the length of a vector. Now we're ready to define the distance between two vectors. Our whole goal in section 6.1 is to start developing geometry for vector spaces. And that has a specific purpose. It's not just because geometry is fun and cool. It's more because of once you have this, a notion of distance between vectors in your vector space, this enables us to do calculus on the vector space. If you're getting into calculus 3, that's exactly what's going on. You're in R3 in calculus 3. That's an honest vector space. It gets imbued with the inner product. That's this one right here. And sure, in calculus, you define your inner product like this, bracket UV, but you're doing the same exact thing. I think they typically would call it a dot product. And one of the things you learn about in calculus 3, once you have that dot product, is how to find distance between vectors and angles between vectors. So let's give this a try ourselves. So here's two basic vectors. These are coming out of R2. We want the distance between U and V. But since this problem is so geometry oriented, let's actually sketch this out. Let's see, both vectors are essentially in quadrant 1 in the plane R2, so I'll draw it out like this. U is 3, 4, so 1, 2, 3, 1, 2, 3, 4. So here's where U would be. The vector V is at 7, 1, so 1, 2, 3, 4. That takes us to 7. Height 1. And there's our vector V. Now, whenever you draw these kinds of vectors, you usually want to consider them with the zero vector as well in the space. Finally, there is really 3 distances we're looking at. There's a distance from here to here. That's just the length of U, written as norm U. There's the distance going here to here. That's the length of V, written as norm V, with that double absolute value bars. And this is the thing we actually want to calculate. This is the distance between u and v. Sometimes our author writes it as a function of two inputs, u and v, in this way. Other times he just writes it out in that format. Let's use both. Distance of u minus v. So that's the first thing we'll calculate, this distance here. And this is the geometry behind the whole problem so far. Let me zoom in just a touch. First, let's do distance between u and v. It's nothing but the norm of u minus v. And so you're pretty much just going to follow your nose on this one. It's order of operations. You have to do the vector addition first, u plus negative v. The notation starts to look a little ugly, though, once you do that vector subtraction. Because we're taking the norm of a vector, or double absolute value bars get really huge. And in here goes the difference. So 3 minus 7 for negative 4. And then 4 minus 1 for positive 3. After we have that, we'll go over here and just calculate it out. Where we ended on Thursday was that the norm of any vector just involves u minus v dot product with u minus v. If you take a vector dot product with itself, you're just coming back here and squaring the entries. So here's what it boils down to. Negative 4 squared plus 3 squared, which is then 16 plus 9. That's the square root of 25. And so we obtain a 5 altogether. So this distance is 5. And we did it, folks. That's the end of that whole problem right here on part A. Any questions or comments on finding that distance between vectors? Okay, now this is the exciting part. Now that we have distances, that's all it takes to begin to find the angle between two different vectors. It says find the angle between u and v. So here it is. There's theta, but of course, when it says find the angle, they don't just mean point at it. We actually want to calculate that thing. And now we have a wonky looking triangle. There's no guarantee of a 90-degree measurement anywhere. We'd have to look into it first. We have a known distance over here, which is opposite of the angle theta. So we can calculate theta if we use law of cosines. So we'll do exactly that right here. So by the law of cosines, well, the first thing you need is these lengths. We need the length of u. So let's calculate norm u. Here's the vector for u. So this is going to boil down to square root of the entries squared summed up. So 3 squared plus 4 squared. That feels like deja vu. That's 9 plus 16, which is the root of 25, which is, again, back to 5. I think it's just kind of rigged numbers to come out, right? That was kind of an interesting coincidence, though. Now, the next one, to take the norm of v, we'll do the same thing. It'll be square root of 7 squared, so 49, plus 1 squared, so 1, giving us a root 50. I'm not sure if we want to reduce it. Let's maybe, well, why not? Let's reduce it, just in case it's helpful. 50 can be factored as 25 by 2. 25 is the perfect square, so we get 5 root 2. So that's this distance going this way, 5 root 2. And then we can finally say, by the law of cosines, that the angle between the vectors u and v, it at least will solve this equation. We go over here and square whatever this distance is. So let's write out, maybe as a formula to start, the distance between u and v squared must be equal to this distance squared plus this distance, or this side length squared, minus 2 times those same values, the norm of u and the norm of v. And then it finally multiplies cosine of that interior angle theta that we indicated at the start. So law of cosines gives us all of this together. That's kind of a random thing to happen in a linear algebra class. The reason we're looking into law of cosines is that's how we're going to define the angle between two vectors. It's this. And all that is a clever reformulation of the law of cosines right there. So we're building that out from scratch. Let's keep on going and see how it comes out as. Left-hand side, we just go over here and square that quantity. So it's 25 now. Equals the square of the norm of u, come over here. We're squaring that quantity for a 25. Plus the square of the norm of v. So that would be, you could square this one, but that involves work. So let's go over here, square the root of 50, and you get just 50. So let's square that answer. Minus 2 times. Now back to the norm of u, that one is 5 from above, times the norm of v. We could put in root 50, but let's put in this one. I think that's going to simplify some of our work. 5 root 2. Multiplying cosine theta. Now finally, we have an equation. We can solve this and get the angle theta. So maybe first thing I would do is subtract 25 from both sides. So they're gone. Also subtract 50 from both sides. So our left-hand side is negative 50 equals the product of all of these. That's 25 by 2. So negative 50 root 2 times cosine theta. Any questions to this stage of the equation? Okay, well, we're just about there. Divide both sides by negative 50 root 2, and we get 1 over root 2 equals cosine theta. That's not the easiest equation to solve on because of this right here is traditionally rationalized. So you might think of it as root 2 over 2. And that helps out a little bit because by pattern recognition, we notice that cosine at pi over 4 does in fact get root 2 over 2, or 1 over root 2 if you have the unrationalized value. So all this work finally tells us theta equals pi over 4 is the angle between u and v. So that's how we make angle measurements. And the really wild thing about all of this is this can be done in a function space. It doesn't have to be done at all in Rn. If you're working in this space and you give it the right inner product, all of this kind of work can be redone. And so you can ask the most bizarre questions like, what is the angle between the exponential function e to the power t and the power function t cubed? So this is pretty much what linear algebra is trying to get into in the sense of all of this leads towards Fourier series and that kind of interesting mathematics. Any questions at all, folks, though, with the main result here, that angle? Okay, one comment I did want to make is, that's cool, we got pi over 4 as an angle, but it's not the most interesting angle we might come up with. The most interesting angle is the one that makes cosine 0 right here. So if theta is equal to pi over 2, then cosine theta equals 0, and we say UV are perpendicular vectors. I like that word, it makes sense. I think most people use the word perpendicular. However, in mathematics, I don't know why, I think people are showing off. They use a different word other than perpendicular. Anyone know the synonym to that word by chance? Oh, sorry, I thought you raised your hands. My bad. Right angle? That would be a good one, absolutely. So let's put that down. I wasn't thinking of that one, but that's a good one to mention. Perpendicular is synonymous with a right angle. Or there's yet another word that you could use here. It's kind of unfortunate. The word that they use in linear algebra and in a lot of other settings, you'll see this in, say, like a calculus book as well, is orthogonal. Orthogonal just means a right angle, a 90-degree measurement, or perpendicular. But for some reason or another, orthogonal is the word that is chosen as the word to describe when the angle between those vectors is pi over 2. We have orthogonal vectors, is what we'll say. But it all means the same thing you might be used to saying, perpendicular or right angles. So finally, This is the law of cosines in its basic form. If you do a lot of clever algebra, you can take this entire equation by the red dot and turn it into this. A lot of little algebraic odds to that spot. It takes some careful work to get to this point, but it turns out u dot v is equal to the norm of u times the norm of v times cosine theta. So now if you put pi over 2 right here, our vectors are orthogonal, and it also means u dot v is 0. And that's the really big takeaway. But this is almost mysterious in a way. We have defined a dot product in such a way that if the dot product is ever 0, and that's a fast computation, we know right away that this is the mathematics that would settle on pi over 2 right here by the red dot. We just don't have to go through all that drudgery. The work has essentially been done with this definition. Some books take this as the actual physical definition of what they mean for orthogonality, that the dot product is 0, and that's their working point. If, however, we have a linearly dependent set, the dot product won't be 0, and we'll say that the vectors are parallel as opposed to orthogonal. So there's a little bit more to unpack here, but we're getting pretty close to the end. Any questions, folks, with those two new pieces of terminology? Okay, well, on example 5, we're just doing more dot products. You can't ask for a more relaxing mathematical operation on week 15, I'd say. We want to know if those vectors are orthogonal, parallel, or neither. So all we have to do is take the dot product like you see up here. So do u dot v. If we follow the algebra exactly as it's indicated, this is what is usually written out. This is u transpose times v. U transpose goes negative 2, 1. V is just 2, 4 copied in. And so this is what the actual algebraic structure looks like. But if you just paired off negative 2 times 2 and got a negative 4, and then did a similar pairing, 1 times 4, and got a positive 4 that way, you're doing the same exact thing. You don't necessarily have to show me the step right here in the middle. This was more just to say once and for all how it's actually really defined. But notice this comes out as 0. And so this immediately implies u and v are, and you could say perpendicular or at right angles, totally up to you, but I'll usually follow the author and say they are orthogonal. And that's done. No law of cosines, no diagram. That's the value of simplifying our work and making the right definition, like the one right up here. We'll try it again on example 6, but any questions, folks, with that first one? Okay, this example already kind of looks shady, I guess because of the fractions. Let's attack it the same way. We can determine if it's orthogonal at least by just taking the dot product. So that's such a fast operation. It might as well be our first step with this. Let's check for orthogonality here. And I'll do it in the shortcut way. I'm just going to take negative 1/3 times 2 plus 2/3 times negative 4. This results in negative 2/3 minus 8/3. And we can essentially just stop right here. This is not equal to 0, which tells us there is no possibility that these are orthogonal vectors at this point. They're either going to be parallel, and we'll have a little bit more to say about that, or potentially neither. This can happen whenever the two vectors that are being given are linearly independent, but not orthogonal. That's the case we'll get neither. Let's actually say that right here for the notes. Occurs when uv is linearly independent, but not orthogonal. So that can happen. It could now either be parallel or neither, but let's get a better lay of the land and just plot the vectors. Sometimes if you could plot stuff, it can really help out what's going on. So here's the sketch of, I'd rather not plot that one, it's just inconvenient. Let's plot this one, 2, negative 4. So here's where the vector v lives. And if we're thinking it might be parallel, one thing that might be helpful for us is, let's actually draw the span of V on this graph as well. So here's V, if we span it, it's every linear combination. That includes the zero vector way out here, and so the graph would look like this. So this is span V. It goes in both directions, so it also is going up this way. And now looking at the vector u, it's at -1/3, so not quite left 1, 2/3, so not quite up 1. It might actually be somewhere right over here. If that's the case, this is when we would say the vectors u and v are parallel. But let's double check that. How can we determine if v, oh, let me make sure I use the right letter. I'm trying to put in the vector u here, so let's use u. Now we want to know, how can we determine if u is actually in this span right here? Well, it would be if the vectors u and v are linearly dependent. So here's the test that we can make right away. Linear dependence would mean they're multiples of each other, but that looks like some math you might have to do. It's just as fast as doing this. Take the determinant of u, v. It would look like this, -1/3, 2/3. For v, it's 2, -4. When we multiply, we'll have -1/3 times 4, so that's 4/3, minus 2/3 times 2, so that's 4/3. This comes out 0, and so that tells us this implies uv is linearly dependent. So that does, in fact, say u must be in the span of v. It's a multiple of it. They're linearly dependent. And it also tells us, finally, u and v are parallel vectors in this case. So let's say our final conclusion. Therefore, uv are parallel. This is what parallel always means in the sense of linear algebra, that one vector is in the span of the other. We never have lines that go this way, because the interesting subsets of R2 are the ones that are actual vector spaces, and they must connect through the origin. So our thought of parallelism is kind of limited in this context, but this is the notion for parallel in linear algebra. We just mean linearly dependent, as opposed to when they're orthogonal up here. And by the way, if you have two vectors that are orthogonal, that's automatic linear independence, some of the best kind. But we did it, folks. This is our test now for whether we have something that's orthogonal or not. Any questions about these problems here? Okay, we're finally getting to the real meat of the notes. And like we mentioned before, example 8 is guaranteed to be the last example on the real final exam. I mean, I changed the numbers, but the concept on example 8 will be the real question. So let's get there. To get to example 8, we have another definition. It is interesting in the sense that it's now a definition about orthogonality. This is the reminder that if z dot w is 0, we have orthogonal vectors, but we want to say even more here. We start with an entire subspace of Rn. So that could be a span of a couple vectors, maybe a single vector in the last problem. And if we find another vector z such that the dot product is 0 for every single vector in the original subspace W, we'll say z is orthogonal to W. It makes sense. It's just a way of saying it's orthogonal to every vector inside W when we say that. Now, that definition there leads to a whole new definition. The moment you put down a subspace in Rn, there is another subspace. It's called the orthogonal complement of W. It's written this way, and it's got a kind of a fancy new symbol. This symbol is sometimes read as perp, for perpendicular or orthogonal. And it's just a way of saying we're talking about the orthogonal complement of W. So this is a collection of all vectors z in the same space Rn as before that satisfies the product z dot w is 0, that inner product, for every vector W lowercase w, and uppercase W. So we want to take every potential vector Z that satisfies that, collect it in here, this is a new subset, and we'll call it the orthogonal complement. It's an interesting set, and we'll try out actually seeing how we can determine if something is inside here by this simple example on example 7. So W is now a subspace of R3 in this problem. We have 3 entries per vector. First question we'll resolve is if 0, the 0 vector is orthogonal to W. Well, only way to know for sure is you have to test it. So recall though, orthogonal to W is a very particular statement. Z is orthogonal to W if the dot product is 0 for every vector in W. So we have to start where it's highlighted in yellow here. That's the easiest thing to miss. So down here, we begin by saying let W be an arbitrary vector in the vector space uppercase W. Arbitrary because we have to show the dot product is 0 for every single vector in W, and we don't necessarily want to list them out for this problem right here. We just let it be any vector. All I know for sure is that it has 3 components if it came out of W, so we can say let W equal W1, W2, W3. It's a vector with 3 components. I don't know what the numbers are because this is meant to be arbitrary. So that's what an arbitrary vector would look like. Then finally, we're trying to resolve this portion. So we're going to take the 0 vector and say then that 0 vector dot product with our arbitrary vector W gives us this. Let's write this out just because it's kind of an interesting product. We transpose the 0 vector, so it's written sideways now with 3 columns, all 0. Multiply it against W1, W2, W3. But now after writing all that out, it almost seems like it was silly, right? You're going to take 0 times W1. It doesn't matter what W1 is any longer. These are real numbers, and they have to obey the 0 product property. It's 0. Plus 0 results in a value of 0. Because we have a 0 right here as a result, 0.w equals 0. And because this was any arbitrary vector in W, we can now conclude that this shows the 0 vector is in, you could write out the orthogonal complement of W if you prefer, or if you like symbols, you can just say the 0 vector is in that. The orthogonal complement of W. I say it the same way either way, but it's a little bit faster to write it in that way, I'd say. We did, folks. That's our first part. It turns out this is always true. Grab any subspace or vector space. The 0 vector is always going to be orthogonal to it. And that might remind you of something. If the 0 vector is inside this set, what else is in there? If it's closed under vector addition and closed under scalar multiplication, it's also a subspace. And it turns out that is true. That is our last interesting subspace for the entire course in linear algebra, but we'll get into those matters next on example 8. Let's do one last thing. The 0 vector is kind of a cheesy one to do because nothing interesting happens, right? You just get 0, but that's more interesting. It's not the 0 vector. Let's test if that thing is inside the orthogonal complement. Any questions whatsoever first, folks, before we give this one a try? Okay. The big challenge with this is you cannot grab a single vector necessarily. I can't just grab this one and just this one, unless we're using a theorem to support us, because the first thing we have to think in terms of is we need an arbitrary vector W. We need one that represents any possibility. We tried it once like this, but that was only suited to dealing with a 0 vector. Now, if we have something that's not a 0 vector, we're going to grab an arbitrary vector by observing W is also the span of a set. That's going to help us out. So let's call this V1. V1 is now 108. This is V2, 1/2, -3 and 4. And if W is an arbitrary vector in uppercase W, let's write that out. Let lowercase w be an arbitrary vector in uppercase W, then just because it's the span of these two vectors, it implies immediately W is a linear combination of the two. So writing that out, that means W is equal to C1V1 plus C2V2 for some scalars C1, C2, and R. So this is now the new way to write any particular vector whatsoever from W. If it's written as a span, we need to go this way because the vector Z we're testing is not the zero vector. And what we'll need next is the algebraic properties that we were looking at on Thursday's class, because every one of those things have to be now used. Well, not every single one, but a lot of them, if we're going to take Z dot W. So this is finally the big step. Z dot product of W is just taking Z dot product with this, C1, V1 plus C2, V2. So there is our arbitrary vector from the vector space W. Now, first thing we can do is use that property. Well, that property says you can distribute a dot product through a sum. It looks kind of wrong because Z is on the left here. But property A also says you can change the order of the dot product. I should actually write that dot product. Sorry about that. That would be considered an omission. To be very clear, you do want that dot product symbol there because it's a non-standard multiplication. So sorry for that mistake there. But because we can switch the order of Z and this vector, it turns out you can really distribute from either side, from the right like you see there, or from the left as you see here. So this turns into Z dot product C1V1 plus Z dot product with C2V2. So that's kind of nice. Here's the first result we just distributed. Now, this dot product is still kind of tricky because of the scalar here. If we want, we can simplify this a whole bunch by using this property. Your scalar, wherever it is, can be moved right in front, right by the red dot. And that's my objective with our last line, is to say it's equal to C1 multiplying Z dot V1 plus C2 multiplying Z dot V2. So all I did in this last step was grab those scalars, which are not in a convenient position, and just move them both out front. I'm kind of out of properties at this point. The last thing we have to do is actually do the dot product, Z dot V1, Z dot V2. So we're done with these notes, but any questions on how we used that theorem one? Okay, I'm going to delete it, but keep in mind it's also up there in the notes, so it's not gone forever. So let's go back up. We need to show what Z is, V1 and V2. So let's scroll maybe to this line. And now we're going to calculate these things in earnest. This is C1 times, we're taking Z. So I'm just trying to choose a color here. This dot product with this. Instead of writing it out, let's use the strategy of eyeballing it. It's going to be 8 times 1, so 8, plus 0 times 0, so 0, plus -1 times +8, so -8. So that's the first one down. Then it's going to be C2. We're on now Z dot V2 here, so let me shift the highlight to that vector. And just like before, eyeball row 1 from V2, row 1 from Z, multiply those corresponding entries, and we're going to get 4 plus 0 minus 4. That's definitely kind of convenient. These are both 0 now, so this equals C1 times 0. I'd rather not use that multiplication symbol because I want to use that bullet to signify the dot product wherever it occurs, just for clarity. plus C2 times 0. So the whole thing was 0. What did we show? We just showed that z dot w equals 0 for every single vector in the original vector space W. That means z is orthogonal to W, and we can summarize by saying, therefore, z is in the orthogonal complement of W. Well, we did it, folks. This is kind of a different problem. It's all about dot products and using its properties. But notice we're also reviewing a whole lot of linear algebra. Things about the span and those sort of related issues keep on coming back. So it's almost a final exam review question in that sense. Any questions at all, folks, before we go to the bigger question, example 8? Okay, there are some good takeaways in this, by the way. One takeaway is that if you're trying to deal with a zero vector, it's orthogonal to everything by its very nature. It's not something you really have to test out. Zero dot product with anything will always result in 0. Another takeaway is if you're trying to find out if z is orthogonal to W, notice what it boils down to. All we really had to do was see if this dot product with that goes to 0. It did right here. And if that dot product with that goes to 0, it did right here. That's the final test of the matter. But we went through the whole process just to show what do the motions really look like. And it also helps us think about span once again. So here are the last big ideas in linear algebra before we run out of content and go to review mode. The first theorem tells us a vector x is in the orthogonal complement if x is orthogonal to every vector in a set that spans W. That's what we were saying. We found that z dot b1 is 0, z dot b2 is 0. Those were the vectors that spanned W, and so that is enough to show your vectors in the orthogonal complement. But this is a bigger takeaway. The orthogonal complement itself is a subspace. And this is the reason why we call it a complement. Whenever you use the word complement in mathematics, it's an analogy. It's kind of a metaphor. A complement is something that's a piece that completes the whole. And this is the whole. The dimension of Rn is n. If you take the dimension of your original subspace, add the dimension of the orthogonal complement, those dimensions will always sum total to n. So that's kind of a nice theorem. But it's really more of a paraphrase and a summary, I'd say. Let me see if I can move something down. Oh, can't quite do that. Let me move this out of the way. Although the theorem is interesting, it's theorem 3 that I'd say is going to be the bigger one for a final exam question, essentially example 8. And this is the theorem. This is sometimes referred to as the fundamental theorem of subspaces. So it's a pretty big deal. But one thing that I feel kind of offended about on our book is they didn't say that. They just called it theorem 3. But even worse, in my opinion, is when you look at the exercises in the book for this section, these are good practice exercises, but not a single one of them is the one we want to calculate. This example 8, relative to this theorem, is not supported by any exercises in our actual textbook. That's kind of rude. But I think it's a very important problem in linear algebra, so that's why I'm giving out that massive hint. This example 8, you can guarantee something like it on the real final exam. It'll be the last question. Well, let's take a look at what it says. It says if you have an m by n matrix, so this is not an invertible matrix theorem problem at all, this is non-square, then the orthogonal complement of the row space of A is the null space of A. That's an interesting statement, but our book didn't do a lot on row spaces. They defined it, but there was hardly any questions that actually targeted it. So I just kind of cut it out of the whole course. It just didn't seem like anything much more than a distraction. For us, this is the bigger statement. I include both statements because I don't want to cut out the theorem. That'd be kind of weird. It's good to just show what the original statement looked like from the textbook. But here's our big statement. The orthogonal complement of a column space is the null space of A transpose. So that's this statement right here. Maybe we can use an arrow to point at it. And in a certain sense, it just looks like it should be right. The column space of A, we want the orthogonal complement to it. All you do is you take that symbol, which says orthogonal complement, flip it around so it says transpose, but you're looking for a null space instead. That's the whole process to actually calculating an orthogonal complement. And if we redid the steps up here, we could show it from scratch, but we're on the last question of linear algebra. Let's treat ourselves and do it through this theorem right here. Any questions before we give it a try? Okay, so let's give this a shot. It's in a real sense, a pretty big review question in linear algebra, because notice it says column space and null space and transpose. So we're surveying lots of different chapters all at once in doing this. Chapter 4, chapters 1, chapter 2 as well. First thing we have to do is, let's consider these vectors. They are in R4. W is going to be the span of those two vectors. And so that automatically says W is a subspace of R4 now. We want its orthogonal complement, but that means we're probably trying to use this portion of the theorem. We need a column space, so let's start by saying let A be equal to W1, W2. So now we have an M by N matrix. We can actually use the fundamental subspace theorems at this stage. Let's connect the dots a little bit more. If W is the span of W1 and W2, and A involves columns W1, W2, we can say then W is the column space of A. And the reason for that is the column space of A is the span of the columns of A. And that's what we did. We threw those columns right inside A, so we forced it to look like a column space. That helps us because now we can say, if W is the column space by the fundamental theorem of subspaces, we can now say the orthogonal complement of W. Well, first, there's this equation. That would be the orthogonal complement of the column space of A. That's a lot of oxygen to say, but faster right. Column space of A, orthogonal complement. Then we go over here and take a look at the fundamental theorem, which says that's nothing but a null space of A transposed. So we want to calculate this right here. So now suddenly we're looking into null spaces. It's always good to remember the definition of this thing. The definition of any null space goes like this. It's the set of all vectors X, such that we have to say A transpose because it's not A going in this time. So A transpose multiplied by X results in the zero vector. But when you really look into a matrix times a vector, that's just a dot product by nature. We're saying that two different dot products return zero. That's not doing anything different than what we did right here. That's two different dot products coming out of zero. We're just doing it in a really fancy format, but the fancier it gets, the easier it is to actually compute the thing. So there's really good value in that theorem. So now that we wrote out the null space, we're a little bit more on track on what we're trying to do. We go to A times X equals the zero as a vector. And we can say that this, A transpose X, equals to the zero vector, has augmented matrix that goes like this. A transpose, augment with X. This didn't really achieve anything, but it makes the notes more readable. So now we know what we're doing. We have to expand all this. So A transpose means, go back to where A was. Transpose was a concept we studied in chapter 2, I believe section 2.1. What it says is you're taking your column, here's the first column, transpose it means just make it a row. So column 1 is now row 1, 1, 2, 0, 3. Column 2 over here on A, because we're doing a transpose, it turns into row 2. So it's 0, 1, 4, 1. It's been augmented with the vector x, or excuse me, I did make a mistake here. Sorry about that. Must be the last day of class or something. I think we're all a little bit tired, definitely me. Let's use green here just to show what that mistake was. When you augment a matrix, you don't put in x, that's the solution. You put in the right-hand sides. That's a really weird thing to goof on the essentially the last section of the class. But don't do as I did. That's a weird mistake to make. Now that it's augmented appropriately, I'm putting 0, 0 here. And honestly, the only reason I knew I made a mistake was I was thinking, wait, what is x? Hang on, that's something we're solving. It can't possibly go here. It's the right-hand sides that go in that location. Okay, we're on the right track. And this is the punchline. All we're doing is solving for a null space where we transpose both of those vectors down here. That means we have to row reduce it to reduced row echelon form. Any questions first to this stage? Okay, it looks like it's a one-step operation. Let's copy down row 2, 0, 1, 4, 1, 0. Then take -2 times row 2, add it to row 1, and that produces 1, 0, -4, 1, and a 0. This is now reduced row echelon form, and so we're back to chapter 1. We're trying to get the parametric vector form for the solution set of that equation. I think that was like section 1.4. It starts to get foggy after a while, maybe section 1.3. So to do that, it helps to write out x1, x2, x3, x4, because we need to know which variables are the pivot variables. They're x1, x2, and these two are the free variables. I said pivot variables. I was thinking pivot columns, but the formal word is basic variables, whereas these are the free ones. So now this row reduced echelon form then implies this row 1 is an equation 1, and we'll solve for x1. x1 equals 4, x3 minus x4. Do it again for row 2. x2 equals -4x3 minus x4. Last two are free variables, so the standard thing we do just to help out with parametric vector form is write x3 equals x3, and last x4 equals x4.
Would it be -4 for x1 and 4 for x2?
Oh, good call on that one. That was definitely a big goof on my part. When you're solving these, you are subtracting 4x3 and x4. Good call. That means that this would be, or hang on, let me double check. Should have negatives. Oh, which line were we looking at? I think I lost track on that thought. Was it this one right here?
Yes.
Oh, gotcha. I think,
The top has the -4 first, minus facing that.
yeah, I added 4x3 for a positive there, and then I subtracted an x4 for a negative x4 there.
Oh, I see.
And then I subtracted on those. But I'm glad you made that comment because I had to double check. I thought I did mix it up myself. These can be kind of tricky just at that stage all on its own. Thanks for taking another look at it. Other questions at the moment? Okay, we're still in chapter 1 on parametric vector form. And when we went to write our answer, we said on the homework problems, in order to get full credit, you have to write out this. It might make sense finally why we paid so much attention to this one step. It was about extracting the right column vectors from here. So we're back to solving this equation, which is producing all x's in that null space. So we can say x, that one by the red dot, is equal to, come over here, pull out the parameter now, x3, and grab coefficients, 4, -4, 1, 0. Then it'll be added to, next parameter is x4, and it's multiplied by -1, -1, 0, 1, just the coefficients from before. And there are no conditions on x3, x4, they are free variables, but it does pay to say one additional statement. X is equal to that linear combination where x3, x4 are in R. This allows our vector x to be all linear combinations of this column vector and that column vector, which tells us we're dealing with a span, and that's good. That's what proves to us the orthogonal complement right here is a true subspace. So now we move backwards. We're here. These are the vectors that go inside the null space. It was the null space of A transpose. And we did all of that because we're trying to calculate this orthogonal complement. So we're going back through that definition, or excuse me, this theorem right here. And here's the last steps to finally calculate the orthogonal complement. Let's say, therefore, the orthogonal complement of W, this is the collection of every single vector that is orthogonal to both of these simultaneously. It's equal to the span. Span is here because it's a reminder there is no limit to that linear combination. This is essentially the span right at the moment. It's the span of 4, -4, 1, 0. And -1, -1, 0, 1. But let me see if I can fix my penmanship down here. We're nearly done. This is the answer, but there's a really fast check. The check is so fast on this, I feel like it would be a huge disservice to not do it on this one. But any questions with the conclusion here? Okay, well, if you really have the right answer, here's how we can tell. Take this vector, it's in the orthogonal complement of W, which means this vector, when you dot product with this one and this one, had better be 0. It's orthogonal, so the angles between them must be 0. Let's test it out. I'm going to take these entries, multiply them against these entries, and we'll get 4 minus 8 plus 0. Uh-oh. Let me take another look. I've got a 4, a minus 8, plus a 0, plus a 0, giving me a -4. That makes me nervous. That kind of looks like I do have a mistake here. Oh dear. Anyone happen to see what went wrong on that dot product? I had a 1, 2, 0, 3 dot product with this one. It's a 4 minus 8, and then a 0 and a 0. Oh dear, I might have a mistake somewhere on these notes. Maybe I'll try out this one. Oh, I'll erase it. Let me try out the dot product of this one with this one and see what we get. We take that corresponding dot product. I'll go along the entries of this vector and this vector. Let's see how this one comes out. That would be a 0 minus a 1 plus a 0 plus a 1. Okay, that makes me happy. We do get 0 on that one. Let's take that same vector and do a dot product right here. Don't know why I changed the color, but let's go with it. So the purple vector and the one down below, that dot product will be -1 minus 2 plus 0 plus 3. Okay, so I've got 2 good results. I should be getting 0 dot products when I take that vector with a check and do the dot product with both of those. But something went wrong on my first one where I'm going to put a question mark. Let's see. Well, maybe I'll try the dot product of this one with this one and see how that goes to start out. So if we dot product in that way, we'll be taking a 0 minus a 4 plus a 4 plus a 0. Okay, that one worked out. Now this is my struggle right here. Something went wrong with the dot product between these two question marks. yet they should become zero if you did everything perfectly. So let's try this one more time. Corresponding entries, dot product. Yeah, that still doesn't look right. That'd be a 4. Then next entry down, 2 by -4 is a -8. The next entry down, I have a 0 here, so it's a 0 for sure. Next entry down is 3 times 0, so a 0 for sure. That is not equal to 0, so I still have an issue on that one. How strange.
I have a question. I mean, in the row reduction, so
Yeah.
there's like in the first row, isn't that going to be -8 instead of -4?
Oh, I think you spotted it. Good call. What I was trying to do is take -2 times row 2, add it to row 1, and I kind of achieved that until I got to here. Thanks for spotting that, Rajab. I don't think I was going to find that mistake in the 9 minutes of class we have left. That was a -8, add to here, resulting in a -8. Let's track these errors through as carefully as possible. I'll use the Omnimus red pen. That one turns into a -8. Let's see what else would happen with that. If that's a -8, then over here, it would have been a -8x3. Or excuse me, plus 8x3 minus x4. So that's an 8. Where else does that go? Well, if that's an 8, it comes over here as an 8. Okay, so if it's an 8 there, where does that go? Well, we dropped it into that location, so this one's an 8. And finally, let's complete our check. This 8 would multiply up here, giving us an 8 in that spot, and then the -8 plus 0, which would result in a 0 dot product. And so now the check is complete. Thanks for spotting that one, Rajab. You saved the problem. I was probably about to give up and maybe come back to it on our review. But you know what? That's a good thing to have happen to you on a final exam. If something doesn't work out, there's probably a simple mistake somewhere. But on a real final exam, don't erase everything, because if you don't find the mistake, it's hard to do if it's your own mistake. You're still getting a lot of partial credit on this problem. In fact, you might have noticed if you're off by a single number, I often don't even take a point off. I'm looking more on the process that you know on linear algebra. But it's good to get it right, so thanks again, Rajab, for spotting that. So our check is complete. And now we're going to come back over here and just answer the follow-up question. We want to know what's the dimension of W. Coming back here, W involves 2 vectors, and they are linearly independent because they're not multiples of each other. We can tell already from row 1 having a 0 entry and a non-zero entry. Those are non-zero. So W1, W2 is the basis if you take out span. There's 2 vectors in that basis, so we can say down below, dimension W is equal to 2. What about the dimension of the orthogonal complement? Well, we can use another idea. These are in R4, and so the dimension of the orthogonal complement of W should be 4 minus whatever number that was. And so it should be 2. But just like before, we're looking at the 2 vectors that form the basis. Just this part without the span is the basis. We can tell it's a basis because it does span and they're linearly independent. So it must be dimension 2. But we did it, folks. That's going to be the last question on the final exam. Any questions at all with getting through these problems here? Okay, I'm going to save these up. And we have a little bit of time, so let's see if we can change gears. Taking a minute to save this one. Even Microsoft Word is a little bit tired, I guess. We're just about done with the semester. And this is going to be the last document that we're going to go through, that review there. I have it posted on the blank lecture notes if you want blank copies of this one. And essentially all this is a bunch of random questions. Some of these came from old final exams. Some of them came from homework assignments, lecture notes, and things like that. I'll probably, when we come back on Thursday, just kind of go down the line. But the one I do absolutely want to make sure we hit before we run out of time is going to be almost there. This one. So we'll redo the problem that we just got through, hopefully with less work double checking we got the right answer. And that will be our extra practice on those concepts. Otherwise, we'll go down the line, but when we come back on Thursday's class, I encourage you all to look through this document. We'll look through other things, maybe old exams, old homework problems, anything at all you'd like to discuss, and we can throw it onto our review document. And so I'm happy to make this as student directed as you like. If we run out of questions, we'll just continue through these problems. Well, we've got about 4 minutes. Yeah, go ahead.
Are the questions on this review document of higher priority than the full bank necessarily, or just a sample?
It's another just a random selection from that full test bank of problems, the blank lecture notes. I would say if I put all these together, it would probably qualify as a new final exam. So think of this as a new version of a final exam that you're not actually going to be given. It's not quite right in length, even though it says 16 questions. I'm writing one that's about 16 questions-ish. Some of these are really long, so this is a longer document than it really seems like. Other questions so far? Okay, well, we've got 3 minutes, and it is a review question, so let's see how far we get on this one. We have 2 random vectors in R3. We want to know for a third vector, 1h1, for what value of h is this vector going to be in the span of v1, v2? These are always tough questions, but here's how you could start thinking about it. Span v1, v2. The more you know about set theory and the more you actually write down these sets, the easier it gets to deal with span. It's this set, c1, v1 plus c2, v2, such that c1, c2 are in R. So that's what we mean by the span of v1, v2, any possible linear combination whatsoever. Now we're wondering, when is y in the span? Well, that's just saying, when is y equal to one of those linear combinations by the red dot? So y in span v1, v2 means x1, v1 plus x2, v2 equals y. We just have a brand new vector equation. You could have used c1, c2 if you like, but these are dummy variables. They could be p1, p2, k1, k2, anything you like. But since we're solving a vector equation, we most normally write it as x1, x2. As a vector equation, it has augmented matrix that goes like this. We ditch the actual coefficient x1 and go and put in a constant vector, 1, 0, -3. Next constant vector, 0, 1, 5. We're augmenting, so we're augmenting with the right-hand side, the vector y, and that one goes 1h1. So if it's in the span, that means this thing right here is consistent. Oh, I should finish off that statement. Means the vector equation is consistent. That vector equation by the red dot. But now consistency is going to be boiled down to where are the pivots on this thing? We don't need row reduced echelon form, just echelon form will do the job. So let me start with 1, 0, 1 in row 1, 0, 1h in row 2, and let me know if my row reduction goes off the rails again. Multiply row 1 by 3, add to the entries below, we'll get 0, 5, 3 plus 1 for a 4. We're on our way, let's copy in rows 1 and 2, 1, 0, 1, 0, 1h. This should be our last step. Multiply this row by -5, add to the entries below, and we get 0, 0. This is -5h plus 4, so 4 minus 5h. Now, the biggest concern we have is this. If that's a pivot, then y is not inside this set because the equation is inconsistent as long as there's a pivot here. So for what values of h is it in the span? That's going to be the value of h that makes this 0. Let's say here, y is in span v1, v2, if and only if 4 minus 5h equals 0, which then would mean h is equal to 4/5. So that's the value that puts you in the span. Exactly one value this time to make that work. Well, we'll take a look at more review questions when we come back on Thursday's class, but it looks like I did run over on the time there. Sorry about that, folks. Any last questions before we call it a day officially? Okay, well, if you also are waiting on your final exam, don't hesitate to email, or not your final exam, your exam 3. Don't hesitate to email. I'll be happy to provide it. And for folks in class, I do have it for you.
Thank you so much, Mike.
You bet. Take care.
Thank you. Have a good one.
You too. I think I already said you. Yeah, you're right. Well, have a good one, folks. See you all on Thursday. Hello. Oh, yeah. Oh, gotcha. Oh, man, that's awful. Is there any one credit summer courses out there for you? Dang it. Yeah. I see. Have you reached out to the people at WSU about that conundrum? They weren't making any adjustments or any of that for you? That's awful. Sorry about that. My high school is pretty terrible too. They barely allowed me to graduate. Oh, that is a weird situation to be in. Sorry about that. I see. Hmm. Oh, man. That is rough that they're not working with you on that. Yeah, but you'd have to be there for a year, you'd say. That's terrible too. It's just too bad that people can't see the situation and just be reasonable people. You know what I mean? Uh, Fiber two? Ah,
Then fill out,